In this module, we will introduce the topic of spectroscopy. In its broadest sense, spectroscopy refers to the study of the interaction between electromagnetic radiation and matter. The two main concepts central to the definition of spectroscopy are illustrated here. The diverse forms of spectroscopy are some of the most powerful tools available to chemists, allowing them to investigate the matter at the atomic and molecular level. Let us first focus on the nature of electromagnetic radiation. This figure depicts a traveling electromagnetic wave accompanied by its associated electric and magnetic fields. There are several key properties that characterize electromagnetic waves. Wavelength lambda is the distance between successive peaks of the wave. Frequency nu is the number of wave cycles that pass a given point per unit of time. The relationship between the wavelengths and frequency of a wave is given by their product, phase velocity. Phase velocity is the rate at which the wave propagates in any medium. For electromagnetic radiation traveling in vacuum, phase velocity is equal to a fundamental constant known as the speed of light in vacuum and denoted as c. c is approximately 2.99 to 10 in the power of 8 meters per second. However, when an electromagnetic wave travels through a medium other than vacuum, its phase velocity is smaller than the speed of light in vacuum by a factor known as the absolute refractive index of the medium. The concept of wave-particle duality, as discussed in quantum mechanics, is an important piece for the understanding of the nature of light and electromagnetic radiation. Historically, light was first understood as a wave, as presented in the previous slide. However, later experiments suggested that light also behaves as if it were composed of discrete packets of energy, or particles. Particles of electromagnetic radiation are known as photons. As such, they carry energy. The energy of a photon E is directly proportional to its frequency or inversely proportional to its wavelength, as given by this equation. Here, h is a Planck's constant. This equation ties together the wave and particle natures of light. The frequency characterizes its wave-like nature, while the discrete energy E encapsulates the particle-like behavior. And now let's take a look at the electromagnetic spectrum. This spectrum is a continuum of electromagnetic waves arranged according to wavelengths and photon energy. The electromagnetic spectrum encompasses a vast range of wavelengths that span from hundreds of thousands of kilometers to sizes approaching the size of the atomic nucleus. To categorize this spectrum, we divide it into several bands. Starting from the longest wavelengths to the shortest, they are radio waves, microwaves, infrared region, visible light, ultraviolet radiation, X-rays, and gamma rays. The visible light, which our eyes can detect, is just a minuscule portion of this entire spectrum. Our eyes are sensitive to wavelengths ranging from about 400 to 700 nanometers. As we move through the spectrum, the energy of photons changes significantly. Gamma rays, for instance, have extremely high energy, while radio waves are at the lowest end of the energy scale. This vast energy range is crucial for spectroscopic techniques as it allows scientists to probe various energy level spacings. In the realm of chemical spectroscopies, the photon energy spans an astonishing 16 orders of magnitude from the radio frequency region all the way to the X-ray domain. Now that we have introduced electromagnetic radiation in the scope necessary for this topic, let us return our focus to the heart of chemical spectroscopy, the chemical systems themselves. These systems, whether they be atoms or molecules, are quantum mechanical systems possessing a discrete set of energy levels. This discreteness is fundamental to spectroscopy. If these energy levels were continuous, distinguishing specific species based on their spectra would be basically impossible. So, how does the interaction between electromagnetic radiation and quantum mechanical systems manifest? When a molecule or atom transitions between two energy states, it either absorbs or emits a photon. The energy of this photon equals the difference in energy between these two states, and it is also equal to the product of Planck's constant and the frequency of the emitted or absorbed radiation. This equation can be seen as nothing else but the principle of the conservation of energy brought to the quantum mechanics level. To summarize, the discrete energy levels of atoms and molecules on one hand, and an equivalence of energy changes in a chemical system to the energy of photons emitted or absorbed, form the foundation of spectroscopy.